In today's video, we're going to be discussing direct proofs, which is one of the common methods of proofs in mathematics. Now, this will be one of many because I'll go over a few of the other common methods in other videos, and this is part of the real analysis playlist that I have on my channel, and you can reference that if you need to as well. So, before we get into anything, it's important to understand that proofs are the backbone of mathematics, and they provide a way for us to establish the truth behind mathematical statements. And there are several common methods of proofs that are used in mathematics. Obviously, one being direct proofs. Another one is proof by contradiction. It's very common when you get into the higher levels of mathematics. Another one is proof by induction. You have existence proofs, and then you have uniqueness proofs. Now, like I said, in today's video, we're going to be focused primarily on direct proofs, and each of these topics will each have their own video further down the line. Now, it's important to understand what a direct proof is. A direct proof is a very straightforward method of proving that a statement is true, and we do so by assuming that the hypothesis is true, and then logically we deduce a conclusion based on a lot of prior knowledge. If you want to make a brief bullet here, it's very straightforward. And then we assume that the hypothesis is true. And on background knowledge. Now, this may sound a little intimidating here. It's typically what gets people, because the higher you go up in math, it's expected that you've had a lot of experience with different forms of math. And so the knowledge that you have should be enough to help you solve or prove certain statements. And so here is the first example that I have. This example essentially states that if 3 times x plus 5 equals 21, then x must be equal to 2. Now, you're probably thinking, this is really easy. I've seen multi-step equations like this all the time. I can do this with my eyes closed. Now, I'm going to ask you a question. How do you know that this is true? That x is equal to 2? Oh, you could just say, well, if you solve it, then x equals 2. Well, true. Now my question is, when you're solving this equation, how do you know that the steps that you're taking are correct? Well, another common answer that you're probably thinking is, because I've done this forever, it's what I know is true. Don't tell me that it's wrong. And I get it, for sure. Now, one thing I want to harp on is that each step that you take in solving a multi-step equation is defined by some law or some algebraic property. And that's how we know that that step is true, because it's fundamentally what we're taught when we're first introduced to math. As we progress throughout math, it's becomes super repetitive and it's kind of like engraved into our brains. So let's directly prove that x is 2. So we have 3x plus 5 is equal to 21. Well, in order to start this equation off, we need to eliminate the parentheses, and we do so by distributing 3. And this method is obviously the distributive property. Oops, there we go. And so then on the left-hand side, we have 3x plus 15, and then all of that is still equal to 21. Then we subtract 15 from both sides to isolate the term 3x. Now, this property is called the subtraction property, of equality, which you should probably already be familiar with. Oops. I'm making a lot of mistakes today. Subtraction property of equality. And then from there, this cancels out, and we're left with 3x on the left side and 6 on the right. And then we divide by 3 to isolate x. And this property is what we know as the division property of equality. Man, I do not like the word property today. Property of equality. And then from there, we can simplify. The 3's cancel out, and x is equal to 2, which is the truth and what we sought out to prove in the first place. Now, obviously, I didn't have to write down all of these properties here, but I wanted to prove a point that we know that the steps that we take to solve multi-step equations are true because of these properties, these fundamental algebraic properties. And when we go into more challenging examples, a similar concept is also true. So let's look at another example. Now we have, if n is an even integer, we want to prove that n squared is also an even integer. Now, it looks a little bit more intimidating than our multi-step equation, obviously, but I assure you, it is much more simple than it presents. What you should be asking yourself is, what is the formal definition of an even integer? By definition, n is an even integer if there exists, so this symbol here, it just means there exists. And you're going to see me use that symbol quite a lot. So n is an even integer if there exists an integer that we'll call k, such that, and this little abbreviation just means such that. So n is an even integer if there exists an integer k such that n is equal to 2k. Now, all this statement means is that even numbers or even integers can be written as 2 times another integer. Well, let's check really quick. So let's think about all of the even numbers that we know. Let's just do purple. There we go. So let's start with the first even number that we know, which is 2. Well, if we want to rewrite 2 as 2 times another integer, it'd just be 2 times 1. Let's think of another even number, 4. And we know that in order to rewrite 4 as 2 times a number, it's just 2 times 2. Let's think a little bit higher. 102. This would just be written as 2 times 51. Now, look at this entire pattern that we have here. We know that according to this definition, we have n, which are even numbers or even integers, and they are rewritten as 2 times another integer. Now, regardless of if the integer is even or odd, it's just another integer. And that's really what I want you guys to focus on for this example, is that if you have an even number, it can be rewritten as 2 times another integer. That's going to be important for proving that n squared is also an even integer. So now that we're familiar with the definition of an even integer, we can take this information and prove n squared is also an even integer. So to find that n squared is also an even integer, so let's start the proof. So by definition of an even, terrible handwriting, Sandy, of an even integer, we have an integer k such that n equals 2 times k. We're basically just restating the definition of an even integer. Let me realign this actually. There we go. 2 times k. Oops. That should be an. Okay. Now, to find n squared, can you take a guess how we would do that? If you say square both sides, you're absolutely correct. So to find n squared, we're just going to square both sides and simplify such that we have n squared on the left and 4 times k squared on the right. Now that we have simplified n squared, we can rewrite the right-hand side of n squared so that it looks like our definition of an even integer, similar to how we did for our more literal examples. Rewrite the right-hand side as 2 times 2k squared. So by definition, we know that 2 belongs out front. We now need to be sure that the expression in the parentheses is also an integer. Well, we know that k is an integer, and an integer squared is just going to give us an integer. So we know that k squared is an integer. K squared times 2, well, what do you think that's just going to be? It's just going to be one giant integer in this parentheses. This entire thing is just one integer. Let me break it down just one more time. So we know that by definition, k is an integer. And k squared itself is also an integer, because an integer just times an integer is just an integer. And now we have k squared, which is an integer, times 2, which we know is another integer. And what did we just state? An integer times an integer is just an integer. So that means this entire term is an integer. That means we have 2 times an integer. And what does the definition of an even integer require? That it can be written as 2 times an integer, which is perfect for what we need to complete our proof. Since k is an integer, 2 times k squared is also an integer. Therefore, there we go. N squared is an even integer if n is an even integer. I'm running out of space here. An even integer. And then I like to end my proofs with the shaded box. You could also write QED if you want, but I think for space here, shaded box is fine. So let's move on to the final example in today's video. We want to prove that if m and n are perfect squares, then m times n is also a perfect square. So very similar to our previous example, we want to make sure we are familiar with the definition of a perfect square. And it is as follows. X is a perfect square if there exists an integer, there goes that word again, if there is an integer, k, such that x is equal to k squared. Basically, this definition states that perfect squares can be written as, so if you have a perfect square, which is x, it can be written as an integer squared. So if we were to adapt this definition for m and n, it would be very similar. We would just have to change what we represent the integers as, since we want m and n to be their own unique set of perfect squares, and we don't want to get confused reusing the same letters in our proof. If m is a perfect square, then that means that it can be written as an integer squared. So we can pick any random letter to represent this integer. I'm going to choose A. So if m is a perfect square, then it can be rewritten as a squared. If n is a perfect square, then we're going to rewrite that as an integer squared. So we'll use B for n. Now, similar to the last example, let's look at some literal numbers and see the pattern. We know that 4 is a perfect square, and it's written as 2 squared. The next one would be 9. That would be 3 squared. Then we have 16, which is 4 squared. We get higher. We know that 121 is 11 squared. A little bit higher, we know that 169 is 13 squared. 196 is 14 squared. So you can see that for each perfect square, that it is true that you can rewrite them as just an integer squared, which is all the definition is stating. You got a perfect square, you can rewrite it as an integer squared. And like I said, for the sake of this example, I want m and n to be different perfect squares, to make sure that we don't get confused here. It's true that they could be the same perfect square, but again, for the sake of this example, we want them to be different. So that means on the left-hand side, we can choose two numbers. I'll choose, I don't know, let's just do 9 for m and 121 for n. And you can, like I said, you can swap these around however you want. You just gotta make sure that m and n are different for this example. And that means that 3 for m would be A, and 11 for n would be B. Sticking with the definition here. So visually, this is what the definition looks like. And of course, this continues forever and ever and ever and ever, but we're not gonna write every single perfect square for the sake of time. So now that we're familiar with the definition of a perfect square, we can begin our proof. And we start the proof by stating the definition. So by definition, m and n are perfect squares if there exists integers, we call them A and B, such that, And then we're just going to rewrite what we wrote before. M is equal to A squared and N is equal to B squared. Now, for the example, we want to show that M times N, that product is also a perfect square. So how can we get M times N? Well, we could just multiply M times N. And since we know that M is A squared, we're just multiplying A squared times N, which is B squared. So using some algebraic properties, or exponential properties for that matter, we can combine the bases A and B, since they're raised to the same power, which is in this case 2. It'd be A times B squared. And now we want to recall what we know about integers. We know that A and B are integers by definition. And we want to make sure that this expression follows the definition of a perfect square. So we know that A and B are integers, and if we look at what the definition of a perfect square is, remember it's an integer squared. A perfect square could be written as an integer squared. So we want to make sure that A times B here is an integer, and we know that it's squared. So we know that A and B are integers by definition. Similar to our last example, we know that an integer times an integer is what? An integer. So this entire thing in the parentheses, this entire expression is an integer. So what do we have on the right-hand side? An integer squared, which is what we needed for our proof. Since the definition of a perfect square is what? An integer squared. So since A and B are integers, it follows that A times B is an integer. Therefore, by definition, M times N is a perfect square. And then that's the end of the proof. Very similar to the last example, we got familiar with the definition of a perfect square. And then we showed that the desired product could be expressed like the definition. And thus, the desired product was a perfect square. I hope this video was very informative, and I hope you guys learned something. If I didn't come across as very clear for certain concepts, please feel free to leave that feedback in the comments below. I will be reading all the comments, and hopefully with time I get more confident making videos like this. I really am passionate about these sort of topics, and I wanted to provide a resource too, because when I was in undergrad and my early stages of grad school, I really didn't have many resources like this for someone to like break it down for me. So hopefully I was able to be that resource for you. And like I said, I take any feedback that I can get. In the next video, we'll go over another method of proofs, and I hope to see you guys there.